Good afternoon, guys. This is Jeremiah with Palm Air Condition, your service manager. Wanted to take another opportunity to speak with you guys on video. What you see in front of you is a couple of thermal expansion valves. Our last couple of videos have involved the coronavirus updates, and we're talking about all different protocols. And I decided we needed to get back and do a little technical training again. And so, just over the last couple of weeks, I've had a couple of technicians have some difficulty diagnosing one of these thermal expansion valves, and in both cases the actual diagnose turned out to be something besides the valve itself. And so I thought it would probably be wise to go ahead and speak on the valve, what it is, what's all of inside of it, what's its main job, and then how to actually diagnose one of these in the event that you actually suspect that one of these is faulty. First thing we're going to do is we're going to look at the makeup of the valve itself. Up top, there's two different valves here. This is an externally equalized valve. This is an internally equalized valve. Up top is your sensing bulb and capillary tubes. The sensing bulb is typically mounted to the suction line, and it is actually charged with a little bit of refrigerant, typically whatever type of refrigerant they're using in that particular system. What happens is that sensing bulb charged with refrigerant attached to this capillary tube actually will exert pressure onto this diaphragm when the suction line senses an additional heat load. So the additional heat load will actually manifest as a warmer suction line. The warmer suction line will increase pressure. We all know that increase in temperature causes an increase in pressure. A decrease in temperature will cause a decrease in pressure. So when that suction line gets warm, it increases the pressure, which increases the PSI inside of this capillary tube, which will push on this diaphragm that we're looking at right here. Same in the internally equalized one. And it will depress the pin against the spring pressure, which, by the way, the spring pressure is typically set from the manufacturer. Some of the larger commercial applications, that spring pressure can actually be set in the field as well as in some of the refrigeration style equipment. However, for what we're dealing with, for the most part, that spring pressure is not adjustable, and it's set automatically from the manufacturer. Where these two valves start to change or differ a little bit is actually how they're equalized. All right, so this is an internal equalizer port. You can see very small little spaces there, which allow some of this evaporator pressure to creep up and assist the spring. Vice versa, this is just same style, except for it's externally equalized, meaning it's got a capillary tube that connects to the same area of the valve body itself, and that is either connected through a flare fitting or compression fitting, or in some cases it's actually soldered or sweated, brazed directly into the suction line itself. A couple things to keep in mind, guys, when we're changing out these valves, or we're changing out coils and we need to move the old valve to the new coil, or we're putting a new valve in with a new coil. A couple things to remember. If the external equalizer is connected with a flare fitting and you're getting a coil from the manufacturer, you want to make sure that the flare connection on the coil itself does not have a straighter core. Typically, the flare connections on these small capillary tubes do not have core depressors, meaning if you leave the core inside of there and you attach the external equalizer to the condenser, the core inside will not allow the evaporator pressure to actually do its job through the equalizer port. So the other scenario is if you are brazing this into the suction line, you want to be sure to push this far enough into the suction line. That isn't the suction line. The suction line would be up here underneath the bulb, but you want to make sure that's pushed far enough into the suction line so that we don't get brazing material inside of the external equalizer tube, which would cause the same effect and cause that valve to not operate properly. The way either one of these two valves work is we're feeding the valve with a full column. Guys, this is very important. A full column of liquid coming from your condensing unit. How do we know whether there's a full column of liquid? Well, we're going to check with subcool. We all know that in a thermal expansion valve type system, a system that's utilizing a thermal expansion valve as its metering device, we always dial in the subcool when we're dialing the charge on that particular system. If you have enough subcool, you can assume that you have a full column of liquid, but just to be 100% certain, guys, when you're taking superheat and subcool readings, we're typically doing those outside at the condenser. Depending on line length and where the lines are ran, there could be some pressure drop or heat exchange between the suction line and the liquid line. So we always want to confirm that you still have subcool at the valve itself. So how do we do that? We basically just take a temperature of the liquid line at the air handler itself, and it should be fairly close to the temperature of the line that we had out at the condenser. 1 or 2 degrees, guys, one way or the other is not a big deal. However, anything more than that, I would start to look for restrictions. Typically, the first places I'm looking for restrictions is usually at the filter line dryer itself. It's as simple as taking a inlet temperature and an outlet temperature and comparing the difference. Most cases I see no difference at all across a filter dryer. Anything more than about 2 degrees, I start to get worried. Anything more than 4 or 5, there's definitely a problem, and I'm recommending the filter dryer be replaced before we can do any further diagnostics. At the end of the day, the way this is working, we're getting a full column of high pressure liquid coming from the condenser, and that's entering the valve. Depending on the heat load that this sensing bulb is seeing and how open this needle or pin is, will determine how much refrigerant we actually get into the evaporator, and that actually is what controls our superheat. At the end of the day, we've got 2 closing forces and 1 opening force. Closing force number 1 is your spring pressure. Spring pressure is adjusted or dialed in from the manufacturer, and it's typically not something that you're going to be changing while you're in the field. It's something that usually is set, ready to go. In some of the larger industrial, as I said earlier, we can actually adjust superheat, and that's typically done with an Allen wrench, which we can actually insert in the bottom. I'm sorry, a service wrench. Oftentimes you'll see a small valve stem. You can actually tell when these are adjustable because there'll be a separate nut right here with a flare fitting that you'll have to actually remove, and then when you open it up, you'll actually see a square screw type adjustment where you can actually put a service wrench on there, and then you can tighten or loosen to increase or decrease spring pressure. We'll talk about how to adjust one of those in another video. Today I just want to discuss the residential thermal expansion valves, which is what we're mostly looking at while we're out there in the field. All right, gentlemen, on this second piece of paper, I've got a couple of examples. As we discussed earlier, there's a few things that need to be checked before you're even looking at diagnostics to determine whether or not a thermal expansion valve is faulty or not. Those include airflow. All right, airflow should be set just the way the manufacturer wants it. There are airflow charts out there that you can actually compare to static pressure to make sure that you are receiving the right CFM. You can also use heat rise method out there to confirm CFM. Those methods we've discussed those methods in the past. I can discuss them again in another video, but at this point that's not what I'm looking for. But what I am looking for is that we've got it set for the proper tonnage, and we've got it set to at least medium airflow, which should give us around 350 CFM per ton. That's typically what we are shooting for in our market down here in South Florida. Once we determine that we do have enough airflow, static pressure isn't too high, the next thing we want to make sure is that we've got that full column of liquid that I discussed. That's as simple as making sure that I've got enough subcool, guys. Most air conditioning units, residential air conditioning units that we're dealing with, are somewhere between 8 and probably about 15. I wrote 8 and 10 here, but anywhere from 8 to 15 is probably within range. Most manufacturers list that on their data tag on the condenser itself. You can see in example number 1, we've got 106 psi. 106 psi correlates with a 34.1 saturation temperature, and my suction line temperature is 44.1, leaving me with 10 degrees of superheat. Even though I wrote 14, I apologize about that, guys. It was a mistype there. At the end of the day, 10 degrees of superheat or 14 degrees of superheat, either way, you're within that range of 6 to 14 degrees on superheat. Some manufacturers might be slightly higher, depending on the type of equipment you're working on, it might be slightly lower, but at the end of the day, I'm within range. I've already stopped suspecting my thermal expansion valve at this point. Instead, we come over here to the other side because, again, we need to make sure that we got the full column of liquid, and we do. We are within range on our superheat between 10 and 14. And you can see my subcool is, well, just slightly higher than what the manufacturer would recommend. However, the next thing that I'm looking at is my temperature difference, my delta T, or my temperature across my evaporator coil. That's 24 degree delta T. With that high of a temperature difference, I'm looking at airflow. Is my fan set properly? Am I getting the proper amount of airflow? Do I have a clean evaporated coil? Do I have a clean filter? Example number 2 is actually our example of an actual faulty thermal expansion valve. Again, you guys can observe exact same suction pressure. However, in this case, my superheat is up to 27 degrees. And my subcool is even outside of range. It's actually a little bit higher. A lot of times guys get thrown off by this thinking, oh, maybe it's overcharged. Well, if it was overcharged, I'd actually have low superheat. That's thing number 1. The other thing is we have to think about what that valve is actually doing. So when that valve, because that valve isn't opening properly, what's happening is it's actually stacking some of that refrigerant inside the condenser. With the refrigerant staying in the condenser longer, I'm getting an increase in subcool, which is why I got high subcool and high superheat, which leads me to believe that this is a faulty TXV. All right, gentlemen, here are 2 more examples. Once again, guys, my suction pressure is exactly the same in both of these examples. What's changing is my discharge pressure. Too often, guys, I get calls from you and you tell me I think it's a bad expansion valve, but I wanna make sure. And you read me off a high superheat or a low superheat and expect me to tell you, yeah, you're right, it's a bad thermal expansion valve. And typically my next question is, well, what's my superheat? And then I start asking questions like, where's my fan set for? What's my static pressure? Where's the unit located? You know, all of those type things. Have you checked your filter? Have you looked at your coil? Do you have eyes on your coil yet? And again, there's so many other factors, guys, that we have to take in consideration when we're diagnosing these valves, that superheat alone isn't enough to tell me if I've got a bad or a good expansion valve, until I factor in the other parts of the system. So over here you can see this is actually an overcharged system. Okay, same as the last 3 examples, 106 psi, leaving me with a 34.1 saturation temperature, but this time I've got 38.1 suction line temperature, which leaves me only 4 degrees of superheat. And my head pressure, you can see, is running a little bit high. We'd have to know the ambient to see if that's really truly high or not. However, it's a little higher than what we typically are seeing out there on a normal day-to-day basis. And yet I've got 20 degrees of subcool with a 20 degree TD. This tells me that that system is overcharged. Too much subcool, so I am receiving a full column of liquid. My thermal expansion valve wants to do its job. However, because it's overcharged, it's actually shutting itself down, causing you to see that low superheat. So that extra liquid that's hitting that valve is actually causing low superheat. So low superheat, high subcool, overcharged. Vice versa, guys. High superheat, low subcool. Now I'm not getting a full column of liquid, which means the TXV cannot do its job. It's open wide open, but still not getting enough refrigerant, even though it's open wide open. And you can see the biggest difference here, guys, is it actually affects my temperature difference now. Here, my valve's doing its job, getting more than enough liquid. Here, my valve's doing its job, however, isn't getting enough liquid, and therefore the evaporator is empty, causing high superheat and a low temperature difference. All right, guys, I'm back. I just want to go ahead and recap what we discussed. We were discussing thermal expansion valves and how to check them in the field. A couple things I want to discuss. We talked about the bulb test, where we actually take a sensing bulb off and actually put it into hot water or into cold water. it isn't my first go-to move. It is something that I will do out there, but typically I'm doing that after I've already determined that I do have a bad valve, by ruling out all of those other things. And then the process of actually taking the bulb off and putting the bulb in hot water versus cold water is actually designed to exercise the valve. Sometimes in doing that, you can actually cause whatever gunk or foreign material is actually clogging the valve in the first place to actually free and cause a valve to work again. In that situation, guys, I am still recommending the thermal expansion valve be replaced, as well as the filter line dryer, just because whatever caused that valve to get stuck could very well end up back at the valve again down the line. So it's always in the customer's best interest to just go ahead and replace it anyway to prevent future problems. I just want to do a real quick recap, guys. Before we are determining whether or not we've got a bad valve, we need to confirm, do we have enough refrigerant in the system? We're going to do that by determining what the subcool should be and what it actually is in the system. When we're checking subcool, we want to do it both inside and outside, and that's the same for superheat as well. We want to make sure that there isn't some huge rise in superheat from inside to outside. I have seen it, guys, where my superheat is perfect on the inside, 10, 11, 12 degrees of superheat, yet outside I've got 20 degrees of superheat. I'm picking it all up under the ground because insulation has deteriorated, or it's ran into a PVC line chase, and over time, however they sealed the PVC has failed, and now there's water inside there causing an exchange of temperature between the warmer liquid line and the colder suction line. So things like that should be taken into consideration, guys. We want to know superheat and subcool both outside of the condenser, where is the best place to take it, or oftentimes the only place to take it, and then take those temperatures at the lines inside again, guys, just to make sure there isn't anything going on in the line. If you do suspect a restriction, especially in your liquid line, go to your filter line dryer, take a temperature on each side of the dryer. Again, guys, I told you 1 to 2 degrees shouldn't be a problem. Anything more than 2 degrees, I get nervous. Anything more than 4 or 5, there's more, for sure, definitely a problem, and we need to replace that that filter line dryer before we can further diagnose the system. Other thing to listen for, to remember, guys, is if you're low on refrigerant, or if there's a restriction in the liquid line dryer, it is often heard at the air handler. You have to have a trained ear for this, but I'm sure many of us have heard the swishing sound of the refrigerant. You've had a customer in the past say, you know what, my air handler is making a funny noise, and they describe it as a swishing noise, or a shh, 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 shh. It sounds almost like water is flowing through the pipe. What that actually is, guys, is that space in the line causing a little resonation through the line, and that can be heard oftentimes at the air handler if your ear is trained for that. The other things to keep in mind, guys, is airflow. Airflow is super important. We're looking for 350 CFM per ton typically, especially down here in our market where we're looking for a little more dehumidification. We can discuss the different ways to check that, but probably your best way to check that was going to be with a magnehelic or a manometer. You're gonna put one probe in the supply, one in the return. You're going to get a total external static pressure. Typically we're looking for 0.5 or below. We probably are okay because most of us are dealing with electrically commutated motors or ECM motors these days. So anything up to about 0.75 static pressure is probably okay. Anything over 0.75 static pressure, I get nervous. Once I hit 1 inch, I'm warning the customer, and I'm trying to find out where that duct restriction or airflow restriction is coming from. Other things to remember when we're talking about airflow: dirty filters, dirty coils, as well as fan settings will all affect airflow. One more thing, guys, I just want to make sure that we remember how important it is to actually complete a full diagnostic. If you're calling me for technical support, I'm going to be asking questions, and they're going to be all answered right on your diagnostic. So please, guys, I would ask that you fill those diagnostics out before you call me. Chances are you're going to figure it out beforehand. Of course, I'm always available, so if you have any questions, give me a call. I also want to remind you guys to remember that there's play from one tool to the next. So from one set of gauges, from one thermometer, from one clamp to the next, there is a little bit of play, which is why there are ranges and not just set amounts of superheat and subcool. And then I also want to talk about some of the different things that actually can clog valves, like carbon or oxidation inside of the copper lines, as well as moisture byproducts, acid, things of that nature, and also different types of additives, corrosion inhibitors. Some of you may remember from a few years ago, I believe it was Copeland changed the rust inhibitor inside of their compressor, which was having a reaction with the 410A, the oil in the 410A, so that oil was actually having a reaction. It was causing these thermal expansion valves to gum up. So some of those things I just want to make sure that we are familiar with. And then I just want to say, last but not least, thank you for all your hard work. Thank you for everything you're doing out there, and hope to see you again real soon. Have a great day.